Io allora introduco il primo dei seminari di oggi, che ha ricevuto un'onorificenza al premio Paladin dell'ultima edizione, devo dire 2025, e una menzione speciale e tra i premi, diciamo, minori c'è quello, tra le onorificenze minori c'è quello dell'invito a fare questo seminario. Allora, il titolo di questo seminario, cioè che sarà tenuto da Mattia Scandolo, è Density Fluctuation. Sorry, I was speaking in Italian, so let me switch to English. So the title of this seminar is Density Fluctuation and Phase Transitions in Active Matter. Mattia is actually a postdoc at the James Franck Institute in Chicago, but is actually now visiting, if I well understand, l'École Normale Supérieure in Paris is there as a visiting scholar. And he did his PhD with Andrea Cavagna in Rome. And he finished the last year. Okay, so please, Mattia, you have 25 minutes.
Okay, thank you. Thank you for the very kind introduction. Let me share my screen, and you should see my slides now, right?
Yes.
Okay, great. So thank you for the very kind introduction, and to the organizers for the invitation, and for all of you for being here. What I would like to talk about today is, as the title already says, what happens when you have density fluctuations and what happens to phase transition in active matter systems. This was a project that was started when I was still a PhD student back in Sapienza University in Rome, but also carried out as a part of it in collaboration with the University of Cambridge during a visiting period I did there under the supervision of Professor Mike Cates. So let me start right away. I guess we're all pretty well familiar with the concept of active matter, and the aspect I will probably focus more on today is the aspect of flocking. So what is referred often to polar active matter. Flocking is that phenomenon whereby a bunch of individuals are able to interact with each other and give rise at a large scale to this collective motion. As a physicist, the mechanism through which global alignment can arise from only local, let's say, interaction is pretty well understood. This is exactly the same thing we have behind ferromagnetic systems. So you think of an Ising, a Heisenberg model or something like that, you have that local interactions give rise to a global magnetization. And very similarly, the same thing basically happens also in systems like flux. One of the first one to realize this analogy could be let's say brought from the world of ferromagnetism and condensed matter to the study of flocking was Witsek back in the 1990s, when he proposed this basically this model in which individuals, birds or whatever, align a degree of freedom, which we can call the spin sigma in this model, which, however, also dictates the direction in which the particles are moving. So it is effectively their velocity, the direction of motion of each individual. And when you study this system and you look at its different phases, sure enough, you recover something that is pretty familiar to people working in condensed matter and ferromagnetism. That is, you got a phase transition between a disordered phase at low densities and high noise levels to a flocking state, basically similar to the phase transition from a paramagnetic to a ferromagnetic state. Despite the flocking phase being a lot interesting on its own, actually what I would like to focus on today is precisely this phase transition between these two states. The reason why I would like to focus on this phase transition is that there are a bunch of systems, natural swarms in the first place, that do exhibit collective behaviors despite lacking completely the presence of collective order. So these are systems that exactly as I discussed before, have local alignment of their velocities, but however, do not display a net collective motion. And because of these features, so they have very strong correlations, but no order, they are believed to be best described as systems on the onset of a flocking transition. So right at the critical point, if you wish. To try to understand a little bit how this transition from let's say, disordered to flocking works, I will now shift my attention, let's say, from this microscopic model to what is known as the tonal in 2 hydrodynamic theory, which is basically a coarse-grained version, if you wish, of the Witschek model. And I would like to try to understand its behavior close to the phase transition. Just to, probably not because probably many people are not very familiar with this theory, I would like just to try to identify some of its hallmark features. So first of all, this is a theory for the 2 hydrodynamic modes of the system, the velocity v and the density field rho. And then the equation, well, the equation for the density is a simple continuity equation. But the equation for the velocity field has, well, many terms, but a couple of them might be recognized as familiars. So first of all, there is this term here coming from a Landau potential, which is the same you would have in a ferromagnet, and is a term that rules basically the transition from the ordered state, the flocking ordered state, when this parameter alpha is positive, to the disordered state when this parameter alpha turns to be negative. And the onset of the transition, at least at the mean field level, happens exactly when alpha is equal to 0. But we will get to this in a second. Other terms you can realize, you can recognize, are probably these bunch of terms which can be identified kind of as a generalized advection term. The first of them is probably the most familiar one, especially if you think about Navier-Stokes equation. That is a term that is telling you that the particles are moving in the direction of their pointed by their velocity field. So that is the term that comes from the fact that the system is self-propelled at the microscopic level. That particles are moving in the direction pointed by this sigma field here. And there is a last feature of this equation, which is the fact that the velocity is coupled to the density, not only through the presence of a pressure-like force, but also to the fact that each of these individual parameters does itself depend on the local value of the density field. And the reason why this is the case is probably better understood. Well, for sure, I will not enter the case of topological interactions, but at least think about the case of metric interactions. So individuals interacting with all their neighbors, let's say, within a given distance. It is pretty obvious that individuals that interact, that are placed in a more dilute region, interact with way less individuals compared to the ones in let's say, denser regions. And hence, it is reasonable to expect that all these parameters might actually have some kind of local dependency on how the network is structured and how many individuals they're actually interacting with. So this, so these are kind of probably the key features I want you to remember about this hydrodynamic theory. So it has a coupling with the density, it has a transition from order to disorder, and it encodes the presence of advection, which is self-propulsion at the microscopic level. To understand the transition in this system, one can first of all approach the problem by studying the homogeneous solution. So you take the system, you take a homogeneous field, neglect all the the spatial derivatives, and study the solution for those equations. The equations are way simpler. Well, the density is simply fixed by the initial condition, and what happens to the velocity is it depends on whether alpha is positive or negative. When it's negative, the only homogeneous solution possible is a disordered solution in which the mean velocity is always 0. When alpha is positive instead, the system spontaneously breaks its rotational symmetry for the velocity field, and collective motion occurs in a spontaneously chosen direction x of the system. So this is the transition basically at the homogeneous level, at the mean. This is the mean field picture we have of the transition, both in ferromagnets as in flux. The crucial difference between ferromagnets and flux is that when you look at the linear stability of this of the theory, of the full theory, with respect to of non-homogeneous spatial perturbations, you find that close enough to the phase transition, an instability occurs. And this instability is known as probably the banding instability, and it's an instability that generates these higher dense the bands of high density that move in this diluted background. And because of this instability, it is known that the transition that in ferromagnetic systems, for example, was second order, but also based on the, let's say, homogeneous analysis, was was believed to be second order at the beginning. Turns out it is actually a first order phase transition. So this means no collective behaviors occur because there is no critical behavior, no large correlations in the system, and therefore precisely, and this instability occurs because of the interplay between the self-propulsion of at the microscopic level and the presence of density fluctuations. So it is this interplay that is responsible for suppressing basically the possibility of having collective behaviors at the onset of flocking in these kind of theories. As I discussed before, however, we do observe collective behaviors in many systems that are not in the flocking phase. And so how is this possible? Well, we can have two possibilities mainly, and we'll try to investigate both in the remaining of this talk. The first is what happens when the density fluctuations are actually weak. And the second is what happens when self-propulsion itself is small and becomes weak. In both cases, you might understand that if it was the interplay between these two features giving rise to this instability, if you render to make one of the two at least weak, you have hopes to recover a second order transition and therefore collective behaviors at the onset of flocking. So let me start discussing the first feature. This first feature was well, the first one probably that tried to investigate what happened at the phase transition in this torn into equations when you completely suppress density fluctuations, which means you render the system completely incompressible, were Chen, Toner, and Li back in 2015, who studied the phase transition of an incompressible flocking theory. And sure enough, they found that through an normalization group analysis, they found that there was a new fixed point that was characterizing the behavior of this theory at the onset of flocking, which means a second order phase transition associated to this fixed point, which in turn means the presence of collective phenomena, collective behaviors occurring at the phase transition. So great. This means that if you actually completely suppress density fluctuations, you do recover a second order transition. But then what happens when you introduce them back, at least introduce back some mild density fluctuations? And this was the question a former PhD fellow of mine, Luca Di Carlo, and myself tried to answer. And we did this by studying a modified version of the Tournian 2 theory, a theory that is known as the Malthusian Tournian 2 theory, which allows for the presence of birth and death processes. What happens when you allow the presence of birth and death processes is that in the continuity equation, you have this source term here on the right, which, well, by assuming you can expand, let's say, in a kind of harmonic fashion, what you end up getting is that the density fluctuations of this system are neither completely suppressed, as in the incompressible case, nor density fluctuations are a hydrodynamic theory on a hydrodynamic field on their own, as in the case of immortal flux, so flux without birth and death processes. What happens in this intermediate scenario is that the density fluctuations are enslaved to the velocity field. And this is pretty convenient for two reasons. So first of all, I would argue this is a kind of an intermediate scenario where the density fluctuations are not strong enough to be a hydrodynamic field on their own, but they're not incompressible, so are not completely absent. And the second reason is that the system is a bit simpler. You don't have two coupled equations. You have only one hydrodynamic field in the system, which is the velocity, and it is manageable, let's say, at least from a computational viewpoint. What is important to stress here is that there is still a reminiscence of the fact that the velocity was coupled to the density in this equation. And it's the fact that this parameter here, gamma 2, is actually proportional to the inverse of the compressibility. So you can access the incompressible, the fully incompressible limit by sending this parameter gamma 2 to infinity. And sure enough, together with Luca, we did this the RG calculation for this theory. And what we found was that indeed, for very large, for zero incompressibility, you recover the same critical behavior that was observed by Chanton and Lee in their paper. So we found the same behavior in the fully incompressible limit. However, what we were able to study at this point was what happens when you introduce some small compressibility in the system. So you allow the presence of small density fluctuations. So this is the RG flow of a bunch of parameters. The one I want to stress more is this mu parameter here, which basically is infinite whenever the system is incompressible, but is finite whenever the system is compressible. So here you have plotted mu over 1 over mu in order to limit it between 0 and 1. And this is this blue curve here. So we started with a very, let's say, weakly compressible system with a very weak compressibility, so it means very large mu. And what we found that the system first in an intermediate regime approached the incompressible fixed point. But after a certain RG time, this is plotted against the number of RG iterations we did in the system, it happened that the beta coupling, which was responsible for bounding, if you remember the potential, bounding the density fluctuations, turns from positive to negative, signaling the fact that fluctuations are now unbounded. And the reason for this is, we argue, the fact that the phase transition is turning actually in a first order phase transition, in which there is a macroscopic jump between two states. So it's not possible anymore to describe this phase transition through, let's say, small fluctuations around a zero average velocity. What I would like to stress, though, is the fact that the system still approaches the incompressible fixed point at an earlier stage of the RG flow. In other terms, let's say in non-RG terminology, what this means is that if the system's size is small enough, small compared to a crossover scale, the RG flow is actually trapped in the proximity of this incompressible fixed point, and the system therefore does exhibit a second order phenomenology with scaling laws associated to it. It is only when you exceed this crossover scale that you escape the incompressible regime and you flow towards the compressible regime with no scaling laws. So despite having some density fluctuations, as long as they are mild enough compared to the size of the system, it is indeed possible to observe scaling laws and collective behavior at the onset of flocking. This is, I believe, the main result we had in this study we did. So now I would like to quickly, in the time I have left, try to see what happens in the second scenario. So when you have a weak self-propulsion. To do this, I will actually not study the case of the Toner 2 theory. I would rather focus, for reasons that I will try to discuss soon, a simpler model, if you wish, which is what is known as the Active Ising Model. So this is in spirit very similar to the Witzek model, despite flocking occurs via a discrete symmetry breaking and not a continuous symmetry breaking. The way the model is built is the following. You have a bunch of particles that can diffuse on a lattice, on a d-dimensional lattice in general, and there is one specific direction. So they diffuse in all the other direction, but in one specific direction, which I shall refer to the x as the x-axis, spins with particles with a positive spins tend to prefer hopping to the right. They have this bias in their hopping rate, and spins with a negative coupling tend to prefer hopping to the left. This potentially gives rise, is the mechanism, this is kind of an advection. So we have that positive spins tend to prefer traveling to the right, negative spins tend to prefer traveling to the left. And on top of that, of course, spins undergo some alignment interactions with their neighbors. It is important to stress that the way this model is built allows for the system to violate detail balance even when the self-propulsion parameter epsilon is set equal to 0. So even when the particles are diffusing in all directions and undergoing an alignment dynamics with their neighbors, you can still build up a closed loop that you can explicitly show that if you travel this loop in two different directions, the probability is different, and therefore it violates one of the main conditions for detail balance to be obeyed. So the system at the microscopic level does not obey detail balance, which means that even in the case of weak self-propulsion, this is still an interesting non-equilibrium system where the effect of density fluctuations can be investigated. So what I did was coarse graining this microscopic system through techniques related to Doi-Pariti field theories, which I will not enter into the details of this. I would like to just provide what are the field theoretical counterparts of all the microscopic ingredients I just discussed. So first of all, you have the movement in space, which is given by the presence of diffusion. So the two fields, rho A and rho B, are the density fields of the two positive spins and negative spins. And in the presence of this bias diffusion, you have this drift term in both the equation telling you that the A particles prefer to travel to the right on the x-axis, and the B particles prefer to travel to the left. Then we encoded the presence of alignment interactions by a simple, let's say, 3-particle alignment. So whenever a particle is encountering two other particles with opposite spins, it tends to align to them. And finally, to account for the presence of thermal noise, thermal effects, we added the possibility of having a random spin flipping. So a particle decides with a given rate gamma to simply swap its spin. The resulting mesoscopic equations we derived through this coarse graining procedure are the following. So here I'm writing them down for the magnetization, which, if you want, is kind of the equivalent of the momentum in the indeterminate two-field theory and the total density. The phenomenology of this system is not exactly similar, but not that different from what one could have in the Witzek model for what we are interested here, meaning that you have a phase transition, the same Landau potential here, with the crucial fact that the linear term of the magnetization is proportional, is dependent on the density. Then you have advection terms, which are explicitly encoded by these two terms, diffusion, and the phenomenology of this system is very similar. It undergoes as well a banding instability in the presence of self-propulsion and this coupling with diffusion. We're interested, however, in what happens, as I told you in the beginning, when we look at the limit of weak self-propulsion. So we send the self-propulsion to 0. When we send the self-propulsion to 0, this is basically an order parameter, the magnetization M, coupled to a conserved density. So for those of you who are probably familiar with Halper and Hohenberg classification of critical phenomena, this might look like Model C. So what is Model C? The Model C is basically a model in which an order parameter that has a Landau-Ginzburg Hamiltonian is coupled at equilibrium, so through the Hamiltonian, to a conserved density. The equations of this system is actually pretty similar to what we had in this active Ising model. You have this coupling between the density and the magnetization in the magnetization equation. But on top of that, you have also this other feedback, which is required by detail balance of the magnetization in the density equation. And this is the crucial difference between Model C and the system I just discussed, these active Ising models. In our case, we don't have this coupling here. And this is what drives the system out of equilibrium, even in the absence of advection, of self-propulsion. This term cannot be generated in any way under coarse graining, under RG. So we concluded that because of this feature, the phase transition in active Ising models cannot be described by this model C in universality class, contrary to what people have conjectured in the past. In order to completely rule out, however, the possibility of having equilibrium behavior, one has to discuss whether this might be described or not by Model A. Model A is the simplest Landau-Ginzburg, time-dependent Landau-Ginzburg equation one can think of. So it's basically this first equation without this coupling between density and monetization. So if this coupling between density and monetization turns out to be irrelevant and flows to zero under DRG, what happens is that the two equations effectively decouple and one recovers equilibrium behavior of an Ising model, basically. Model A is
you are going to finish your time, yeah?
Yes, I'm almost at the end.
Yeah, okay.
So what I would like to conclude saying is that what we did is looking at the study the RG of this system, and interestingly enough, we find that a new fixed point emerges. A fixed point that this is an epsilon expansion, so a perturbative expansion performed close to 4 dimensions, and epsilon is the deviation from the upper critical dimension. And the exponents we find are different from the one would have expected if this was Ising behavior. To be sure that this is actually holding all the way to the physical case of 3 dimensions, we were able also to come out with a non-perturbative argument, or better say an argument which is valid to all orders in perturbation theory, telling us that very similar to the Harris criterion, telling us that whenever this combination of exponents here is larger than 0, which is the case for 3D Ising, the coupling with the density is expected to be relevant and hence change the universality class of the system, which means leading to a new non-equilibrium universality class, even though self-propulsion is weak. So, okay, with this, I would like just to conclude, hoping that I convinced you about the relevance of density fluctuations, or rather their absence, and how they play a crucial role in shaping collective behaviors in active matter. I leave you here some references about the works I've discussed so far, and I'm glad to take any questions if they are. Thank you.
Thank you, Mattia. Thank you very much. And I think there is not so much time for questions because we want to respect our times, but we have times for 2 short questions. Yeah, please,
okay.
Francesco.
Ciao Mattia, very nice talks. Thanks a lot.
Thank you.
I just was curious, since you're working with my kids, you will surely know, they also, with Etienne Fodor and other people, they propose what they call thermodynamically consistent lattice model,
yes,
where they claim that, if I remember correctly, that if you take this 0 speed limit, you recover model C, right?
Yes, yes.
So I wanted to just understand which is the difference between
the crucial
your
difference
approach and their approach, and where the things may merge.
Okay, so the crucial difference between these two systems is the way the diffusion works. So in these systems I was studying, what you have is that the diffusion, the rates at which particles hop on the lattice. So basically, the mechanism that gives rise to the movement in space are completely independent on the state of the system, on the magnetization of the spin of the particle and the local magnetization. And it is precisely this fact that allows you to build these two loops between the same states, which have different probabilities, and therefore violating the Kolmogorov criterion for detail balance. What they studied instead was systems in which the rate of diffusion is dependent itself on the magnetization in such a way that this detail balance condition is obeyed when you turn off the advection. So that is the crucial difference. If you think about it in terms of equilibrium systems, you can imagine like an equilibrium system not on a lattice, but where if you take two particles, two spins, for example, and you try to pull them far away one from the other, you would naturally have that the interaction between these two spins changes as you change the distance. So that is kind of the system they are studying. In the system I was looking, this is not the case. So two spins getting further apart one from the other have no energetic cost of doing that.
Okay.
Okay, thanks a lot.
And yeah, I'm sure that there will be other questions, but I can't allow you then. Maybe you can write Mattia and
Yeah.
ask him by mail.